show we have Elizabeth Pierce. She's been a visiting lecturer in geosciences at Wellesley College since 2012, and she studies glacial processes, sedimentary record, and the paleoclimate of Earth's polar regions. Elizabeth attended Williams College, majoring in geology, and then obtained an MA, MPhil, and PhD from the Department of Earth and Environmental Studies at Columbia University. Her broad research interests are in the field of paleoclimate, evolution of the East Antarctic ice sheet over the past 34 million years, with a specific focus on mid-Miocene climate transitions. She has developed a method for argon dating of detrital biotites and also employs uranium, lead, zircon analyses and neodymium isotopes and major trace elements on the terrigenous fine fraction sediments, which are typically less than 63 microns in size. Welcome, Elizabeth.
Thank you. Thank you so much for having me.
Perfect. So tell us, as a woman in science, what do you think was your inspiration to get into this field?
I don't know. I showed up my first year in college and I didn't know what I wanted to major in. I liked all of my classes equally, but I do have two parents that are scientists, so I'm sure that had something to do with my early interest. My first year I took a class in oceanography and I just fell in love with learning about how the Earth worked, and I guess the rest is sort of history. So just a passion for learning about the Earth, and I had fantastic professors at Williams that really encouraged me to learn, encouraged me to go to graduate school, and that's pretty much what the big motivation was.
So were you one of those students who tested out the giant flume in the sedimentology lab?
How have you heard about the giant flume?
I know all about the flume.
You know about the flume? Yes. So I was the first class that tested out the first flume, and we had a bit of a malfunction that day, and the hose detached, and it just sprayed water all over all of us.
Perfect.
Yeah, so the flume is there. I'd love to get one of those at Wellesley. I've been talking to Katra Monica, who you've had on the show before, about getting one of those at Wellesley. Yeah, no, the flume is great. There's a lot of cool hands-on stuff we could do there. Yeah, it's a great department there, so that was one of the reasons. And I always knew from a pretty early age that I wanted to teach in one way or another, and so going to graduate school, getting a PhD, and being able to teach was another motivation.
And what field are your parents in science?
My mom has a degree in chemical engineering, and my dad's got a degree in biochemistry.
Wow, those are very sciencey fields.
They are sciencey fields.
You had a lot of STEM growing up.
I guess I did. I never really thought about it, but I think maybe we talked about this, doing paper chromatography with leaves and grass in the backyard, and just sort of
that's not an everyday experiment.
Not an everyday. I guess not. I thought it was normal,
would have their children do in their backyard. Right.
I thought it was normal. So yeah, but they love the humanities and the arts too. So I felt it was a very well-rounded.
Yeah. Especially
childhood.
if you can say chromatography before the age of 10.
Yes, and I could.
That's a good test.
Yeah.
Sounds good. So did you take a lot of science classes in high school?
Yeah, we had sort of a basic physical science class first year, and then I took chemistry, and then physics and AP physics, and a lot of math. So I always had a lot of fun with those. So yeah, definitely a good amount of science before I got to college, and then once I got to college, I took a lot of science.
And did you feel encouraged as a woman taking science classes and being in the science field?
Yeah,
to proceed with that?
I think in high school, once I got to the AP physics level, yeah, I was the only girl in that class with all my guy friends, and so it was a lot of fun. But I never felt daunted by that. And then in college, being a woman in science, it did not strike me as odd at all. I think my senior year, probably more than half of the graduating seniors were women as geoscience majors. And then at the PhD level, more than half of the incoming class were women. In my specific field of paleoclimate, I don't actually know the numbers, but it always seems like there are a lot of women around, so it doesn't feel skewed.
And do you still keep in touch with people who you graduated with? Are they still in the science field?
Yeah, it's sort of a variety. So there are a good number of double majors as well. So let's see, a couple are in finance on Wall Street. I think two of them are in med school. One of them is completing a PhD at Boston University. So I'd say half science, half not science.
That's really interesting. I knew quite a few geologists who went into finance.
Yeah.
I don't know what the connection
Econ
is,
geology was a popular double major
I
my
guess
year.
you can see with mineral resources.
Yeah,
and mining and
exactly.
It's a good tie-in, right?
Exactly.
So did you have a specific mentor, either in high school or in college, that you really loved and got a lot from?
Oh gosh, that's a hard question. I mean, high school, all my teachers were really fantastic. College, I'd say the geosciences department is small. It's like being at Wellesley, so we had 5 or 6 faculty. But yeah, Paul Carabinos, who's my thesis advisor, so I did my senior thesis with him, was really great. And Rona Cox, who owns the Flume that you were talking about. They're just so passionate about, I mean, all of them are, they're just so passionate about teaching and getting students excited about learning about the earth. And I think looking to them and sort of seeing them as something that I wanted to be when I grew up, definitely was the case.
Awesome. And what was your work at Williams in geology for your
So yeah,
senior thesis?
I did. Yeah, so my senior thesis, it was local geology. So we were basically out in Western Massachusetts, and I counted thousands and thousands of quartz pebbles that had been deformed about 400 million years ago when you had a convergent plate boundary along here. So forming the Appalachians. And the idea was that if you start with a pebble that's round and it gets deformed and it's nice and long, you can actually measure the 3 different axes of the pebble and say something about how much strain occurred and in what direction it was. So it required doing a couple weeks of field work the summer before my senior year, and then doing some work with smaller samples in the lab.
So for the layperson who might be wondering how that's done, so this is not like going out in the field and just randomly collecting quartz pebbles and counting them,
No,
right?
no. So this requires planning in advance. So we got out a geologic map that some people had put together over the decades, and we saw where the specific quartz pebble conglomerate, so it's just quartz pebbles that are essentially glued together.
So it's still in the large rocks, it's still attached.
Yeah, exactly. It's still a massive body of rock, and we look and see where that's actually cropping out at the surface. And so we targeted certain areas. We went out in the field, went to the specific areas, recorded the location, and then would start measuring pebbles that were actually in an outcrop. And so we did that at probably 30 locations, and then in some cases we actually would take a hand sample, which is what it sounds like, a smaller piece of the outcrop that we'd hammer off. And we took that back to the lab, and so we could look at sort of smaller deformational structures back there.
Awesome. Sounds interesting. So did you ever feel in college, so through undergrad or grad school, that your courses and classes got really tough?
Oh.
And decided, well, maybe I should think about quitting and going to finance.
Quitting and going into finance. No, I never thought about that particular path. I think the courses at Williams were all very challenging, and graduate school also challenging, but you had a really good support network with other students and the college itself. And so, no, once I latched onto the geoscience major, that was kind of it for me. And I think in graduate school, the transition then is going from taking courses to doing your research. And that I found very challenging, sort of your self-directed learning, but that's also a skill now that I truly love. I learn something new easily every day through teaching or my own research. So yeah, that was the most challenging part, but I never thought about leaving geoscience for a different field, no.
Because I was reading this article about especially women who think they want to be scientists or go into science fields. They get to college and they realize that the courses are way too difficult and they weren't adequately prepared in high school. And they decide to drop out of that and switch to something else.
Yeah.
So I just wanted to get your perspective on
how
much of that is going on and how it's prevalent.
It's going on, for sure. I felt very well prepared for college from the school that I went to in high school, and so while the courses were challenging, I didn't feel like I could never do this. And I think there is a bit of a focus now too on, there is a correlation between how well you perceive you do in a class with the grade you get versus your actual understanding of it. And so often students, and I see this all the time, if they don't get the solid A, they think I'm not good at this, therefore I'm going to go find something else to do. And I think that right there is the heart of the problem. And so trying to encourage learning for learning's sake rather than just getting that A, and having the A being a measure of success is sort of the key to all of it.
And in our modern environment, how well do you think geology or geology majors, the field itself, correlates to getting jobs?
I think it's good. The geosciences, I mean, most students, I usually pull my intro students and I say, have you had earth science in middle school? And maybe half of them will put their hands up. I'll say, if you had it in high school, 2 of them will put their hands up. So in terms of having exposure to the earth science before you even get to the college level is very, very small. And so as a result, unless you're in, Texas, for example, where there's a big oil industry, being a geology major is definitely, you're in the minority there. Like I said, there were 10 of us my senior year. The following year, there were 2 of us. But in terms of getting jobs, you're thinking on amazing time scales and spatial skills, so your reasoning and thinking about big processes and even small processes is really good. And so like I said, there are people that are in the medical profession, finance, academia, teaching. So no, I think it's definitely a good degree to have, and just in terms of knowing how the world around you works, I think that's something every citizen should have an understanding of.
Yeah, I had a friend of mine, a professional geologist, who said to me that geology will make a comeback once we colonize Mars. And we start our mining processes up there, so it'll be like discovering the West again.
I think geology is definitely, it's true, right? It's the next frontier, and I've been reading about, there are a lot of studies coming out about Mars now, and evidence for water, and people that study Mars definitely have a very strong geology background, so you can be a planetary geologist and sort of combine the two of them. Especially with climate change in the news, and people are becoming much more aware of needing to understand how the Earth works.
And it's interesting, I read recently that there's one of the moons of Jupiter that has an Earth-like, possible Earth-like environment.
Yes, I read that too, but I could not comment on it any further than I read it, and it was very interesting.
Sounds good. So tell us about your work and your interest in geochronology. And radiogenic isotopes.
Excuse me. Yeah, so like you said at the beginning, I'm really just interested in how the icy regions of Earth have evolved over the past 65 million years. And so we've got a whole suite of evidence that tells us that widespread glaciation first occurred in East Antarctica, which is the bigger part of Antarctica, about 34 million years ago. And whenever we're studying past climate change, we can't directly tap into the record, so we need some sort of proxy to measure it. And through these various proxies, we have a general sense of what sea level has done over the past 34 million years, an idea of temperatures. It's a bit spotty in some places. And so, but for ice sheets, we actually want to study sort of where they evolved, where they grew on the continent. And 98% of the continent's covered in ice, so we can't actually just go and walk around on the continent and look for glacial features that we might be able to do in North America. And ice sheets also they erode their own history. They're very destructive. So even if we could walk around on the continent, it would be kind of hard to study. And so people that study long-term ice sheet history tend to look at marine sediments, so sediment that gets dumped into the ocean by icebergs, for example. So I'm getting back to the geochronology point, I promise. And so I just use geochronology and isotopes as a way to fingerprint sediment that the ice basically dumps into the ocean. And so for the argon isotopes, we use that to date minerals, get an actual age, and so it's the age of the rock where that mineral came from when it formed. And then neodymium isotopes, the values that you get on the fine sediments just going to be a function of the initial composition of that rock. And so basically we want to see, okay, we've got Antarctica, can we divide it up into different source areas and then trace sediment that was dumped in the ocean back to where it came from? And that'll inform us about where the ice was growing, where it was retreating.
So for instance, the original ice sheet might have been partly in India and then attached to Antarctica. And then, so do you find traces of like different continents that it may have come from?
So for sure. So I mean, India separated. So India crashed up into Asia about 55 million years ago. So that is one of the thoughts for actually sort of initiating the cooling phase that we have in the last 65 million years. But yes, the geology of East Antarctica, essentially you've got kind of a 3 billion year old craton. Earth's 4.56 billion years old, so really old craton. And you've got metamorphic terrain sort of around the edge. And yes, we can definitely link up where India used to hook up to East Antarctica. Yeah, and so by looking at the types of rocks and the ages, we can use that to sort of reconstruct Pangea.
Oh, so interesting. And then you have a new way that you've developed with detrital biotites.
Yeah,
dating as well.
so you can date different minerals with different systems, and argon dating is something we can do in minerals called hornblends, which is something my PhD advisor really pioneered for looking at this glacial marine sediments up in the North Atlantic. And then we thought, well, let's see if we can find another tool for fingerprinting the sediment, because the sample sizes that we work with sort of fit in the palm of your hand, and a very, very small fraction of that's sand. And that's the result of actually drilling to recover the samples. We're not going to an outcrop and taking a huge sample. So we've got hornblends in there. We thought, well, we see a lot of biotites too, so why don't we try that? And so we took samples that were collected around the continent. We pulled out the biotites and dated them with the argon method and compared it to the previous hornblende results, and it looks like it works really well. Yeah.
And so why hornblends and biotites out of all the minerals that you
Out of all the minerals? Yeah. Good question. So biotites, a lot of people actually might be familiar with. It's sort of the platy mineral that you can peel apart like book layers. Hornblende and biotite are both what we call major rock-forming minerals, and so you would expect to see a pretty high concentration of them in most types of rocks. And so if you think about a glacier scraping over bedrock, picking up material and transporting it, you're going to want to pick something that's sort of ubiquitous.
So there's like a 80% chance that there'll be a hornblende or biotite
It's
somewhere
not
in there.
quite that high, but yeah, I mean, certain types maybe. But you want to pick something that is going to be a relatively high concentration, so you'd expect to find it. And then both of these minerals we can use with the argon-argon method. And so the basis for the argon-argon method is actually an isotope of potassium decaying to argon. And so what you want is minerals that have a good dose of potassium. And so hornblende actually doesn't have quite that much, but it has enough. And then biotite has a lot of potassium in it, which means that there's a lot of argon.
Right, and the actual methodology would be to irradiate both a known sample as well as your field sample.
Oh, we're going to get into
Right.
argon dating.
So
Yes,
right, and then you would measure
exactly.
it that way.
Yeah, so the original method of potassium and argon, you're looking at potassium 40 and you're looking at argon 40, and argon's a gas, and so you'd need a split of your sample, 2 mass spectrometers. You've got huge sample sizes, errors on both of them. With the argon-argon method, you're just measuring argon. And the argon 39 is what we create by sending our samples to a reactor and have them bombarded with fast neutrons. Exactly.
And that would be that. So you'd have a control sample, so you'd have a known rate of decay to measure, and then you compare that to your sample.
Yeah,
and the
because
difference is what you're measuring.
Essentially, yeah. So we have the samples that we're going to date, that we're going to throw the neutrons at them to create this 39 argon, but there's no way to actually say how much we're creating, so we do have this other mineral with a known age that we irradiate at the same time to sort of control for that.
Awesome. I'm sure everyone wants to hear about this because they're wondering, how do people actually date things? It's just fascinating.
Yeah.
So unlike carbon that has a much shorter time frame,
Yes.
so hornblendes and biotites have a longer.
Much longer, yeah. So yeah, radiocarbon, you can go back about 40,000 years, which seems long, but on Earth history time, it's not that long.
Very short.
Right. And with argon dating, you can date the age of the Earth, so you can go back much, much farther.
Awesome. How far back have you found results?
The oldest, yeah, we found some biotites that were 3 billion years old,
nice.
which is pretty cool. So right off the part of Antarctica, that's known as the Groundhog Complex or Grunhogna Complex, and it's actually part of an old craton that you can connect up into Africa.
And is that because that area of the world is relatively intact from like maybe the very first supercontinent?
Oh, so yeah, I mean, it's remnants of really, really old continents. So a lot of it gets recycled over time. But yeah, we still have very old cratons in most of our continents that have survived, which is impressive.
So have you actually spent like a time at McMurdo?
So I haven't been to McMurdo. That's the big one. Yeah. So I spent, I did go to Antarctica in 2009 for about a month. We didn't go to McMurdo, but we stopped at Palmer Station. So I flew down to Punta Arenas in Chile, and then we took a boat across the Southern Ocean and the Drake Passage, which most of us were a little bit queasy, some very queasy.
I hear they're rough waters. And
really rough
air
waters,
currents
and we got through it, and we thought, yeah, we did it. And then the crew said that's the easiest crossing we've ever had. So it took a couple days to get across, and we stopped at Palmer Station, which is one of the tinier U.S. stations right along the peninsula. So we were there for about a day, hiked around on a glacier, saw some penguins, and then we went up towards the tip of the peninsula and then through the Antarctic Sound down into the Weddell Sea. And there were some islands right there that we wanted to go to collect some samples.
Oh, nice. Well, that sounds like fun.
It was amazing. Yeah, if anyone ever has a chance to go to Antarctica, they should definitely go. Say I can carry rocks and I like the cold. So
did they put you through a crevasse rescue training?
No crevasse rescue training.
Did you have to prepare for it?
No. So for my trip, I just had to have like a medical checkup to go down there, and they're very careful about your wisdom teeth. Actually, mine had already been pulled, but you can imagine if your teeth get impacted while you're down in Antarctica. Getting you back out, it's a little hard.
To get back out.
Yeah. So we do, when you go and do research in sort of faraway locations, you usually have a safety team with you. And so Raytheon, I don't know if they're still the ones that do it, we have contracts with the U.S. Antarctic Program. And so every research group, there were 4 of us on the ship doing different but kind of related projects, had like a field camp manager who was supposed to make sure that you don't do something stupid in the name of science. And so
give us some examples of interesting things that people have done in the name of science.
Oh gosh.
Were there any on your group,
any
on your
our
team?
Group? We didn't do anything too bad. One of the problems was when we went down there, the sea ice was so bad that it was actually, and moving really quickly, we didn't get a camp for the full time we were down there because they were worried that they would, put us in the Zodiac, take us to land, and then they wouldn't be able to come back and get us, and we would be stuck on
there.
land for however long.
Right.
So we just did day trips. We did one day where I think we did a 12 or 13 mile hike, but you have to remember as we're going, we're taking rock samples and putting them in our packs.
So you're getting heavier as the day
getting heavier
progresses.
and heavier, and you're trudging through the snow and the slush.
13 miles with rocks.
Yeah, no, it was a good workout. Yeah, I slept all the next day. So we didn't do anything too stupid. I think one study I always talk about with my students when I'm talking about this very topic is if you read about the exploration of the South Pole, and there was sort of this race between the Norwegian team and the British team, and the British team lost Scott, and they died on the way back. And one of the big things is the approach they took. So they were actually, they didn't use sled dogs, they were actually hauling the sleds themselves.
Oh my.
And as they were coming back, Scott was like, we should get those rocks for the scientists. And so they're dying on their way back from the South Pole, and they load up their sledges with rocks. And so that would be a perfect example of something not to do.
Wow, that's quite a commitment.
Yeah, it's a fascinating story actually. To read about sort of the particulars of the exploration in Antarctica, because for a while that was sort of our last frontier.
Exactly. Yeah.
So yeah.
And I suppose the other team didn't collect any rock samples.
No, they were
science.
they were on their cross country skis with their dog and went in, came back out. They were very efficient. Yeah.
Things we do for science.
Yes.
So tell us about some of your work out in Lake Mono, California. Much better climate.
Much better climate, yes, very nice and warm. Yeah, so Mono Lake, it wasn't directly a part of my PhD research, but my PhD advisor, Sydney Hemming, does a lot of work out there, and it's actually a beautiful location just to the east of the Sierras. And it's what we call a closed basin lake, and so
it's a very popular place for sample pulling.
It is
all kinds of different things.
All kinds of different things. It's in the news a lot, yeah. So it's a really interesting water chemistry. You have these calcium carbonate towers, the tufa towers, that are often a tourist destination. And what the group I was a part of when we were sampling is basically trying to figure out how lake level has fluctuated in the past. And so if you imagine it sort of like a bathtub, and you have the water sitting in a certain area, and then you lower it a bit, you leave a ring right there. And so imagine that we have what we call paleo shorelines are forming. So if you can see what the elevation of a shoreline is and date that, you can get at what the lake level was in the past and use that as a proxy for precipitation in that area over time. And so yeah, you've got the tufa towers, you've got some volcanic craters right there.
And you have an anoxic lake bottom as well, and there's some very interesting bacteria that live there as well.
Yeah, and we're getting into territory I'm not familiar with, but yeah, there's some very crazy bacteria that live right there. Yeah, absolutely.
Awesome. So yes, how about Norway?
Norway, I went.
That way as well.
Yeah, I went to Norway. That was a lot of fun. So up towards the north, I went with my office mate, who was at the time just finishing his PhD. He also is interested in the polar regions on much more recent timescales than I am, so I usually look at millions of years. What we were doing up in Norway was basically trying to get a better sense for how ice has been retreating since the last glacial maximum, and the way we can do that is a process called surface exposure dating. And so basically you have cosmic rays coming into the atmosphere, and you get this spallation chain, which basically means that at the surface of the rock you can create certain isotopes that will then start to decay. So beryllium-10 is a very popular method for surface exposure dating. Basically, if you take a sample and you determine the age, you can say how long it has been since that rock was last covered by thick ice. And so you can use that method to actually trace how quickly the ice has been retreating.
So you're not actually drilling ice cores, you're actually
not
looking
ice
at
cores.
the rock.
We're actually looking at the rock, exactly.
Okay. And why is that fraction of sediment useful or most important for your work, the under 63 micron?
Oh, okay, so going back to the IRD, so the less than 63, it's important. The coarse grained material is also really important. So for the minerals that we pick out, we take greater than 150. For what we call the fine fraction, it's less than 63. And there are a couple of reasons for that. One is that if you're out in the open ocean and you find coarse grained material, there's sort of one of two ways you could actually get it out there. And we can determine that ice is a good mover, right? Wind is not going to take a cobble and take it all the way, a couple hundred kilometers offshore. So when you have that sandy material, we know it's an iceberg. The less than 63, well, the iceberg will bring some, some of the sandy and the fine grain material with it, and then just sort of local erosional processes, water flow will bring it out there. And so when we're looking at the mineral grains, we know for sure it's an iceberg transport. When we're looking at the fine fraction, it's sort of a mix of everything that's going on.
So you actually look for them together, and then you take the smaller size
Exactly.
fraction to analyze.
Exactly. So if we have a sediment core that's drilled by the drilling program, and we'll have a hunk of mud, and it's got all sorts of different grain sizes. And so what we'll do is we'll actually sieve it through a series of sieves at, you know, a millimeter, 150 microns, 63 microns, and we'll separate it out that way. And we'll just throw different tools at the different processing.
And that's different from what you did up in Norway, for instance.
Yes, yeah, and then so Norway, you know, the overarching question of what's the ice been doing is still the same, but for Norway, we're actually trying to date when the rock was last covered by an ice sheet. So if you get a series of dates on bedrock that's right in front of a glacier, you can actually calculate a rate of how quickly it's been retreating.
And so the sediment size isn't that important? Or
no, there
there
are various methods.
Yeah.
You can drill into bedrock. Some people use small explosives to get out some rock. It's we did some drilling and some hammering. So yeah.
Sounds good. Pretty safe. No explosives. So tell us about why the mid-Miocene. Why is that all the rage these days?
All the rage these
days,
is it so, according to me.
Yes, so popular to
it
argue over.
actually is gaining some traction, right? So the mid-Miocene climate transition happened about 14 million years ago. So like I said earlier, widespread glaciation in Antarctica is 34 million years ago. We clearly have ice there today. 14 million years ago, based on other information we have, is sort of the second major step in growth of the ice sheet. So up till 14 million years ago, it was still pretty warm. We have these sort of major increases and decreases in ice volume. And then we have this cooling phase at 14 million years. The reasons for that cooling phase are, we have some ideas, but still unresolved. And then some people argue you get into a slightly more stable East Antarctic ice sheet. And so the Pliocene actually sort of 3 to 5 million years has been all the rage a lot because much warmer. We can sort of compare the Pliocene today, what is sea level doing back then. The reason I got interested in the mid-Miocene is looking at these sediment cores that have been drilled off of Antarctica, and we have sort of 2 locations that actually have really good recovery of material. And we see something unique in these sediments that we don't see at any other time in the past 23 million years, which are huge cobbles this big that have just accumulated in the sediment. And so earlier we were talking about hornblends and biotites in the sand fraction. So usually with IRD you get some sand, maybe a few little granules, but we actually have cobbles right then. So that sort of indicated that something interesting was going on.
What do you think it was?
What do I think it was? So basically, right now we're hoping to submit our paper soon. Is that you know, up until the mid-Miocene, you've got this very dynamic ice sheet going back and forth, grinding up lots of material, and then at 14 million years, you have this cooling phase. The ice sheet is growing outwards, and it's basically taking all of that unconsolidated material with it. The way ice sheets work are pretty complicated. It can be hard to study, right? You can't go under an ice sheet and see exactly what's happening, but studies have shown that if you have an ice margin that's being very dynamic and moving back and forth quickly, you can actually incorporate a lot more material that way. And so we just think it was just this really interesting period in the ice sheet history, incorporate a lot of this material, and icebergs carry it out into the open ocean.
So it's like a sudden and a faster sort of climate change that was happening.
No, yeah, it is. It's one of the major steps, major climate changes. So it's a cooling period, not a warming period, but it is a fundamental change in how the ice sheet behaves, we think, through this transition. And we really don't have that much information about this transition. There's a lot of work that's been done in the Dry Valleys region, but otherwise, you know, the continent's covered in ice, and so looking at the marine record is what we have.
The World Bank report just put out a newsletter about why making the Earth's temperature 4 degrees, changing it by 4 degrees, making it maybe 4 degrees warmer is a disastrous sort of condition globally. So what do you think are the impacts for the layperson that we could learn from research such as yours about future possible climate change, and are we really heading to 4 degrees?
Right. So yeah, I'm not up on every single scenario of the projections for sure, but no, warming Earth in terms of the icy regions, that's one of the big questions we're really trying to study. A lot of people have thought East Antarctica to be very stable in the past. Some recent research our group has done in the Pliocene has shown that we do get retreat in certain areas that could raise sea level by a couple meters or more, which would, for this area, obviously be a really big deal. So what we're trying to do with this research is, for sure, use the past to maybe say something about the future. The mid-Miocene is a cooling period, not a warming period, but we can still infer from that sort of where the ice is moving and where it's growing. So we are trying to help with thinking about the future for sure.
Awesome. Wow, that's a lot of information. Thank you, Elizabeth.
Thank
It's
you.
been lovely.